Okay, so I've worked out some properties of homomorphisms. I'm going to introduce a new word now, which is isomorphism. If alpha is invertible, that is, alpha is a bijection, it's one-to-one and onto. Let me just draw that for you. If there's a set G and there's a set H and there's some elements in here, and alpha maps them from one to the other, if it's like that, then I can just draw the lines going backwards from all the elements of from all the elements of H back in to their pre-image in G. So I can invert that because I can just follow the arrows left or right. So that's invertible. Speaking rather loosely here. One-to-one. If it's not one-to-one, you can't do that. If you've got a set G and a set H here, which look like this, that goes there, this is the map alpha here, and those both go to the same element, like that. This isn't invertible, that's not invertible, because you can't follow the function backwards. If you can follow it backwards from here, yep, sure, it came from there. But if you're here, where have you come from? You might have come from this point or that point, you don't know. So it's not invertible because it's not one-to-one. And onto means you haven't got a situation like this. No, I've drawn that the wrong way around. Let's try that again. You've got a set G and a set H, and it might be one-to-one, might look like that, but this point hasn't come from anywhere, so it's not onto. But if it's both of them, if it's one-to-one and onto, then it just looks like this. Might be more complicated. It might the map might look like this, might go up and that might go down, they might cross over or something like that. But this is one-to-one and onto, which is called a bijection. And if you have alpha being a homomorphism, by virtue of its group operations, its behaviour under the group operations, and also alpha is a bijection, then alpha has a special name. You say alpha is an isomorphism. Isomorphism means, well, I guess homomorphism means same shape, but isomorphism means even more same shape in some sense. So I'm going to give you an example of two isomorphic groups. Here's one, 0, 1, 0, 1, and there's my operation star. There it is. Of course, that's just addition modulo 2. And here's another one, A, B, little circle A, B, A, B, B, A. So of course alpha maps, this is group G and this is group H, maps G to H as follows. Alpha of 0 equals A and alpha of 1 equals B. These two groups here are not the same. They are not the same group because they've not got the same set. This is 0 and 1 and that's A and B. But they are the same by virtue of alpha being an isomorphism. So you say that G is isomorphic to H. They are the same group really, I've just written them differently, and you express that notation by saying that the groups are isomorphic to one another. So quite often you say that there's only one group, well I may as well say it, there's only one group of order 2, which is namely this one here, and you say up to isomorphism. You do not want to count these two groups as different when they've got the same structure. They're the same group, something's the same, But they're not the same because the set itself is different. And so you say that they are isomorphic groups, and then you say that groups that are isomorphic are the, in scare quotes, same group. So isomorphism means same group, basically. I'm going to stop there.